So we're going to start with our integral properties. There's three of them, but kind of maybe start over to the edge of your paper because they get long like this way. And they're all pretty intuitive. So draw your integral symbol. And I know you guys are still getting used to that symbol. Looks like the symbol on a violin. If you have integral from a to a, f of x dx, and you have to write f of x dx on every single one, f of x represents the height of the rectangles, dx represents the width of the rectangles. Remember our Riemann sums, it's base times height or length times width, whatever you want to call that. But if you start at A and accumulate area until A, how far did you go? Nowhere. So you get precisely nothing. That ends up being 0. And these do make sense. They're very intuitive. I like these properties. They are going to look a little weird, but they make sense, right? Second one, integral, bless you, from A to B, f of x dx equals negative, or you can think of that as, bless you, the opposite of the integral from B to A, f of x dx. So like, look at it and let it sink in. If you accumulate area forwards, that's opposite of accumulating area backwards. Remember, all of these integrals are area underneath a graph. You're accumulating area, but does that make sense? If you go backwards, it's opposite. Okay. And then the third one, integral from A to B, f of x dx, plus the integral from B to C, f of x dx, equals, and I ran out of space, I'm going to have to go down to the next line. But what do you guys think that equals? If you accumulate area from A to B plus B to C, it's good. Integral from A to C, f of x dx. Again, this all like logically makes sense. So we're going to apply those properties to question 1. So we're going to be given some information, and I'm just going to read through it. Just look at integral from 3 to 6 for x squared dx is 63. It's just true, right? Integral from 3 to 6 of just x dx is 13.5. Again, just true. Now this one, do you see how it's from 3 to 6 and it kind of feels like there's nothing there? Like everything else in mathematics, if there's not a number written, what is it understood to be? 1. So what I would do is put like a little 1 inside of that integral. It's like a 1 dx. Like if you see an x by itself, it's a 1x. Like it's just a 1 in there. All right, so read letter A. Oh, I'm sorry. I didn't go back and change those boundaries. Can you change the boundaries? I want it to be from 6 to 3. I changed a few things on here and I forgot to change that. I'm sorry. I apologize. You guys can handle it though. All right, so do you see how inside the integral it's the x squared? So we're going to look at this one, the one that has the x squared. But this one says from 3 to 6. So if we want to go from 6 to 3, what do you think the answer is going to be? Negative 63. You guys are brilliant. That's all you got to do. It's just opposite because you went the other direction. Now B, you could do it without rewriting the problem, but I want you to understand like how this breaks apart. So I am going to have us write the middle step just for this one. So for this first part, you're allowed to take coefficients and bring them outside of the integral. Let me stress this because I don't want this to be a problem later on. You can take coefficients outside. You cannot take a variable. A variable has to stay inside. With me there? You can take the coefficient outside. So this first part, you can write it as 2 integral, and I'm sorry, I want to change the boundaries. It's 3 to 6. I apologize. 3 to 6 x squared dx. I need to, when we're doing our break, I'm going to go back and change that so I don't have it messed up. All right, minus 5 integral from 3 to 6 x dx. So do you see how I have the minus 5x? I just took the 5 and put it out front. Plus, and then it would be 4 integral 3 to 6 of just dx. Or if you want to put the 1 there, I do kind of recommend that. I think that helps. But do you see how I broke it into 3 separate integrals? And you could probably have figured it out without me doing that, but I just want you to see how it gets written because the notation is half the battle. All All right, so for this first one, you're gonna have 2 times what? Good, 63. And then the second part, it would be minus 5 times, what do you think? 13.5 plus 4 times 3. Good. And I think I tortured you enough with doing arithmetic on the warm-up, so we'll leave it at that, okay? But if you were forced to battle your way through that, you would have to. Okay? Is it? Yeah, right. Thank you. See, we're looking on the bright side. All right, number 2, we're going to use this graph to answer all the questions. All that means is, instead of being handed these numbers like you were in this one, you have to find them yourself. So let's do a real quick recap of how to find areas of some basic shapes. I'm going to just do this verbally. Area of a rectangle. Base times height, length times width, whatever you want to call it. Area of a triangle. We'll get there. 1/2 base times height. Area of a circle. Now they aren't going to give you a full circle. A full circle is pi r squared. Half a circle would be 1/2 pi r squared. And I've also seen them do a quarter circle. That would be 1/4 pi r squared. Okay. And then a trapezoid. 1/2 height, base 1 plus base 2. Okay, so let's go through and find all our areas on here. So this first one's a triangle. And again, this is why I like this material so much better, is because it's very visual. Like, hey, look, guys, that's a triangle. Do you know what I'm saying? Like, you can see it. So that would be 1/2 base times height. What's the base of that triangle? 5. Very good. And the height? No. It is just a distance of 5, but negatives are going to come into play, so hold on to that idea. And then the height is 4. So 1/2 times 5 times 4. 10. Good. That is 10. I'm going to put that right there. Now we have a semicircle, a half circle. So it's going to be 1/2 pi r squared. Pi r squared is a whole circle. We just want half of that. What's the radius of that semicircle? 3. So what would that give you?
4.5.
Well, let's do a fraction. It'll be 9 pi over 2, or 9/2 pi, but this will actually be negative. It will be negative 9/2 pi. Why do you think it's negative? Below sea level. It is like a unaccumulation. And then lastly, we have another triangle. 1/2 base times height. Well, the base is 1 and the height is 2, so that's just 1. Now you're going to just use all those numbers to answer the question. So again, it's exactly what we just did in question 1, except instead of being given those numbers, we had to figure them out ourselves. But we just did, and now we're good. All right, integral from -5 to 0. What do you think? From -5 to 0, I'm just pointing to it. 10, don't overthink it, that's 10. From here to here, do you see what I'm saying? The area is 10, you're accumulating area. All right, B, from 0 to 6. Yeah. -9/2 pi. Letter C, integral from 6 to 7. 1. That's just each of the shapes that we just found. All right, now we're going to start putting them together though. Integral from -5 to 7. Now that's the entire way. You add them all up. So 10 plus 1, 11 minus 9/2 pi. It's just 10 plus -9/2 pi plus 1. It's just the whole thing. Now this one has an absolute value. That means you're going to treat all the areas like they are positive. So what do you think? From -5 to 7 is the whole thing. 11 plus 9/2 pi. See, it's very like common sense sort of thing. And then we've got from 0 to -5. Now, a little tricky there. If you go from 0 to -5, you are accumulating backwards. So it will be -10. All right, so for these last two, we don't have a graph. So we're going to have to create the graph ourselves. All right, so that's just not given to you. So we're going to graph this function that's inside the integral, the 1/2 x plus 2. That's kind of like welcome back to Algebra 1 class. Do you remember lines, slope, and stuff like that? So you would start at 2, 0, 2, and then your slope is 1/2. So that means you're going to go up 1 over 2, up 1 over 2. So it is going to look something like that. And your picture is not going to be perfect because you're just drawing yourself like a quick sketch on your paper here. It's just so you can get a visual and then we can get the area underneath it. So now we only want the area under the graph from where to where? -2 to 4. So here's -2. 1, 2, 3, 4. Here's 4. So this is the area that we want. So we just drew the graph and we're getting the area from -2 to 4. So what shape did we end up with there? It's a trapezoid. Look, if you turn it on its side, this is the height of your trapezoid. All right. So area for a trapezoid, 1/2 times the height. So how many units is this height? 6, good. And then you add the bases together. So this is the first one. How far is that? That's just 1 plus, and then you've got this one, which is 4. I think we could work that out. That's not too terrible. 1/2 of 6 is 3 times 5 is 15. Yeah, so that wasn't too bad. That's all areas. Integrals are areas. That's what we're finding. All right, an absolute value is going to be a V shape, but this one is not centered very nicely. This is going to be more fun with fractions, but it's not going to be as bad as that warm-up one. It's going to hit the x-axis at -4/3. How did I get that? Why would it be -4/3 where it's value? And if you set that equal to 0, or somebody said it's on the inside, anyway, -4/3 is -1 1/3. It's going to be, you know, about there, -1 1/3. And then the V shape is going to go from that. Now you can plug in as many numbers as you want, but what are 2 good numbers to plug in, do you think? Because there's 2 that we really should plug in. Good, why 0 and -3? Because that's correct. Yeah, those are your boundaries. That's the endpoints of your interval. So if you plug in 0 to this, what do you get? 4. So we get 0, 4. That's going to be this part of the V shape. And I mean, the graph would keep going. I guess you can make it keep going if you want to. And then if you plug in -3, that'd be -9 plus 4 is -5. But when you absolute value that, you get 5. So it'll go like this. So the area that we want is the part underneath the graph. It's the area under the graph. And so we get what shapes? Triangles. Looks like little kitty cat ears. But yes, exactly. They're not the same. One's a little bigger than the other. Oh, but extension question. If they were the exact same, you could just do one of them and then double it, which is what I'd want you to do because that makes your life a little bit easier. All right, area for a triangle, 1/2 base times height. Now the height for this first one's 5. That's the easy part. We already plugged in and got 5. What do you think the base is? Because this didn't land like right exactly in the middle. 1 2/3, which would be 5/3. Plus the other triangle, 1/2 base times height. The height is 4. We found that. That's, you know, the easy part. What's the base for this one? It's 1 1/3. So I heard somebody say it back there, 4/3. Pretend you had to get through that. It's not too terrible. That's why I'm going to make us do it. What would this first part give you? Hint, it's a fraction. 5 times 5 is 25. Good. 25, 6. 2 times 3 is 6. plus 4 times 4 is 16, 2 times 3 is 6. And if you add those together, what is that, 41? 41 6.